Hello, 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 hello. Okay, good afternoon. Yes, all right. Hello, Chris. Hello, Paulina. Hello, Katie. Hello, Yavi. Hello, Stephanie. Hello. Awesome. Uh, hello, and uh, sorry. Good afternoon. Good afternoon, Emily. Hello, Shawnee. Good afternoon, Shai. Good afternoon, Fariel. Good afternoon, Marilyn. Good afternoon, Michelle Q. Good afternoon, Brooke. Good afternoon, Harrison. Good afternoon, Freddie. Good afternoon, Katie. Good afternoon, Jada. Good afternoon, Michelle F. Good afternoon, Allison. Good afternoon, Yavi. All right. Good afternoon, Paulina. All right. Good afternoon, Victoria. And good afternoon, Maria. All right. Okay. Maria is very it's scientific language for I'm saying it twice. Okay, let's just get happy with okay, thank you. Me too. I'm not sure okay, I'll take it. Thank you, Chris. I'm not even sure oh wait, I'll take it. Uh I love physical health too, which I haven't seemed to have had since 1969, but uh which is really fascinating because I was born in 70. Okay, so let's just get going. We're gonna keep going over. We're gonna, I believe, stop me if I'm wrong. Hold on a second. Wait, are we recording? Yes, yes, yes. I believe that the last thing we did, pardon me, was we just went through very carefully problem number one of home. Yeah, actually, it would be fire. And yes, you should talk to me about that. I'm always for that. Like, I don't think today is the day, although in a way, today, well, it almost should be because I'm so out of it physically. But no, you should do that. This is the usual thing of we never know whether anybody's joking or not. But like, no, and it's not just him or Michelle. I mean, it's because he's asking. Well, it might be Michelle. I don't know. No, no, no. It is actually a good idea. I actually am a believer in that. We should talk about that, whether it's formally or informally. And again, I mean, he's the one asking. So I'm answering him, Chris, but it's not just about him or something. That's actually a really good idea. Anyway, and I almost just want to make you do it today because I'm so, but I don't think that's fair that would be a nightmare for you to do it unprepared. I have made that mistake in the past, and it ends up being, even for the strongest souls, it ends up being very upsetting for them and for others. But yes, anyway, okay. Oh my God. I'm gonna warn you right now. Today is the day to get me off the topic because I'm so, but don't, please, but do, but don't, but do, but don't. All right. Anyway, we're going back to homework one. Michelle have more hope. Yeah, that's nice. That's nice, Shy, actually. And Chris, well, in some ways, okay, see, oh my God. What could go wrong is you could end up like me. Do you want that to happen? You could end up just like flapping in the verbal wind as I do. Uh, uh, no, I think, okay, I'm just gonna keep going, but yes, and in some ways, that's right. That's right. I mean, if Chris and well, not that Michelle really lacks in All right, I'm going to shut up. See, don't do this. You're kicking a man when he's down. You're taking advantage of an old, crusty, vulnerable. Oh, dude. But we have Felix for that, people. Okay, we're going to go over homework 1B. We're going to continue going over homework 1B. You're going to correct me if I'm wrong. But I believe we just got through question one yesterday. Again, partly because I'm trying to be very carefully show everybody the 5-step method. For some people, this is old news. For some people, it's new news, but it's important news for everybody. And again, for everybody, the 5-step method is super annoying. It is super annoying, and maybe even objectionable when you think you already know the answer. I'm acknowledging that. When you think you already know the answer, nobody likes doing the 5-step method. When you think you don't already know the answer, the 5-step method is your life raft. Whether you believe me at this point or not, it's your life raft intellectually because it gets you much closer to the answer, especially when you think you don't even have a clue what the question means, which happens a lot in physics, and as we go further in this class, tends to happen in this class. The 5-step method, when you don't think you know what you're doing, when you don't think you know what to do, it's the thing that saves you and gets you a lot closer to the answer. But also for those people who are not familiar with it or, don't like it yet, it also just gets you a bunch of points, even as you're not getting the answer. Like it's academically, it cushions you. because it gives you something to do to get points and to keep going. Like even when you think you're clueless, okay? But it only works. I know I've said this a million times, but I just can't say it enough. The 5-step method, it's meant for when you don't know what's going on. It's not meant for in a way where when you do know what's going on. But the reason I'm forcing everybody to do it, even when they know what's going on, is because the life raft that you need when you don't know what's going on can't be built or won't be ready in time if you haven't practiced building it under calm conditions. It's like a fire drill, actually. It's literally like a fire drill, if that helps. Okay. So, but and I'm just saying all that again to say I don't have any illusions that people think it's fun and I know it feels kindergarten-y, but that's what physics feels like when you can't do physics. And what we need is kindergarten techniques to get anyway. All right, enough of so I'm gonna go on with homework 1B. I'm gonna go on with homework 1B. I'm gonna go to question 2. I'm going to, for a little bit while longer, and you can definitely tell me in the chat for like maybe a question or 2 longer, I'll do the 5-step method again, just to make sure everybody's cool with it. But then of course, eventually I'm going to start just sort of moving to writing down answers or writing down whatever thoughts I need. I'll still expect you to do it, but I'm just demonstrating it for a little while first so that we're all on the same page. Also, last point about the 5-step method for people who haven't emphasized it much in prior classes or whatever. The other thing about it is that it is a grading rubric. Like it's really good for you to know it, even if you don't like it, because then you also know like how I'm grading or when I grade, like how or why I'm taking off points when I do. Like if I just take off -2 somewhere and I just write WIQ, if you've done the 5-step method enough, then you'll know I'm just saying, wait, what's the question? Right. But if you do, so it just makes everything more transparent and sort of like hopefully feel more fair or clear. Hopefully. Okay. Well, that's actually a boost of serotonin. Wait, I'm actually gonna wait. Oh, okay. I'm actually looking. I'm looking in the chat because actually this almost looks helpful to people that no, I do not, in fact, lack. No, Michelle totally does not lack competence. I mean, I wouldn't even joke about that. Michelle definitely does not. Well, I don't know if she's saying competence or confidence, but she definitely does not lack competence. Wait, just a second. 5-step method. Yeah, I mean, and Maria, okay, I'm going to dwell on this again for a second. And again, I know I'm like Mr. Defensive. I know. I don't know why. I'm like the used car salesman of physics. Like, I don't know why I feel like I have to defend it all the time. Well, because a lot of people hate it. That's why. Uh, but what Maria's saying in when she says that the 5-step method keeps her from going crazy by making her draw silly little pictures, like obviously even that's like a cute thing to say, but it's actually a deep thing to say to you, honestly, because like it's actually kind of the thing about the 5-step method. Again, to my mind, everything is a metaphor for getting through this science program, right? I'm like trying to teach you how to get through physics, but partly as a metaphor for getting through this science and future science programs, which kind of kick your butt, right? Like kick my butt for sure. Like the science program is designed to make you feel small and make you feel like you don't want to go on. I shouldn't say it's designed, but it does feel that way. I feel like it's designed that way. I don't like that fact, but it feels like it's very gatekeepy. Science in general is very gatekeepy. And so what I'm trying to teach all of you is tricks for going on and crashing through the gates and not letting the gates stop you. And many of those tricks really involve, in effect, what Maria just said in the chat, which is you always have to have something to just sort of keep you going until the next big insight or revelation or answer comes to your mind. That is like a huge trick for all of us. Because and a lot of people that have these tricks make it seem to other people like they always know what's going on, which then decreases other people's confidence. Like seriously, like a lot of people come across like they always know what's going on because they're always working or whatever, they're always having answers. And then everybody else is like, oh God, well, if that's what it's supposed to look like to be in the science program, like to always know what's going on, like I sure don't feel like I always know what's going on. So I guess I don't belong here, or I don't belong in this homework assignment or this class, or I'm going to quit, right? But what some of those people are doing a lot of the time is they just have tricks for continuing to move forward during the periods of not knowing what's going on. And I'm not saying Maria doesn't know what's going on, like far from it. But I am saying, yeah, like even in an exam or in a homework, to have something to do to keep your pen going and keep your brain moving forward while it's waiting for answers to come is like actually super powerful. Really is. Last point on this, as long as I'm back now, it's another one of these days. You know what the summary of all my stupid pep talks or like my preachy, whatever about getting through this program again? One of the summaries of all this stuff is, please don't fall into the trap that we all do all the time. The trap of like everybody, but especially of science students, is what we continually do if we're not careful, is we compare our insides to other people's outsides. You follow me? Maybe I've said this before, but I think it's really important. I didn't make this up. Like, I'm not giving myself credit for this insight, but when someone first told it to me, it knocked my socks off. Like, what we're constantly doing is comparing how we feel on the inside about our confidence or our answers or our questions or whatever to what everybody else looks like. And of course, all of us wouldn't have gotten this far. We wouldn't be in this science program if we hadn't spent decades training ourselves to look like we got our act together on the outside. Like, that's what we all do. We all have a million ways of presenting as though we have our act together to professors, to colleagues, etc. Right? But then we all fool ourselves. Like, then we're all right. But like on the inside, we all feel like panicked. Oh, not everybody. I certainly do, as you can tell. Right. So just keep remembering that the way you feel on the inside is not you. It's not fair for you, whoever you are, to compare the way you feel on the inside to the way everybody else looks on the outside, because they're doing the same thing. Anywho, all right. Oh, Lordy. Sorry. See, if I compare it to where I feel on the inside to the way you look on the outside, I would compare it like a black lung. I mean, in the traditional sense, not in the, oh God, I would like compare pneumonia to intelligence. Okay, my knowledge is, yeah, most people's knowledge is just up front. Sorry. Okay, yes, I'm going back. Yes, fair enough. Yes, I'm going back to the homework questions. I'm sorry. No, thank you. And sorry. Yes, I'm totally going back to homework questions right now. Okay, but thank you for that feedback. Yes. All right, so I'm going back to the homework. Okay. And more feedback on the direct homework will come. It will come. Yes, I owe you that too. But let me talk about the homework right now. That will help also. Okay. All right. So sorry. Homework 1B. Question 2. Okay. So again, we have the diagram. I'm doing the 5-step method right now. Now, if you're doing the homework, you don't have to keep drawing the diagram every time. I'm redrawing it quickly right now because like it's a new class. You could always just say refer to diagram above. Sorry. Okay, that's the diagram, right? So if you were doing the homework right now, there's your step 1 diagram fact pattern. Again, if it's in your homework right now, you don't have to keep redrawing it. You could just say see diagram above. Okay. Then step 2, we're talking about question 2 here. Question 2 is at x equals 0. No, sorry. At x equals x0. What is it? Correct me if I'm wrong, but I believe that is question 2. What is A? At x naught. So now we go to step 3. GDP, general definitions and principles. I'm looking. Acceleration of the mass. Yes. Okay. Thank you, Shawnee. Right. So we're solving the acceleration of the mass. Right. Good. And yes, you will get more feedback. I hear you about the feedback. So step 3 GDP. What's our step? Well, the GDP now is this. Newton's second law. Right. It's still true that F equals negative KX. That was the GDP that we used for question 1. But now what we have to introduce is Newton's second law, which is like almost always true. And it's and when in doubt, if you ever write this down as a GDP, you're going to get points. It's always true in this level of physics. It's always true, and it's almost always relevant somehow. So you would never like lose points for writing this down. It's just a question of whether you're going to end up using it or not. And we are going to use it here. Okay, so we go to the next page. Stop me if I'm just trying to catch up here. Yeah, good. What Shawnee wrote. Yes. Okay. So we go to step. And well, just notice one thing. Notice the way I write it, right? First of all, it's a vector equation. I put vector symbols over the F and the A. It's a vector equation. So what that really means, if it's a vector equation, it really means that it is three equations in three axes simultaneously yet independently, right? The fact that it's a vector equation like means direction matters, yes, but specifically it means that if you add up all the x components of forces acting on the mass, you'll produce the acceleration of the mass in the x-axis. And independently yet simultaneously, if you add up all the y components of forces, you'll get the acceleration of the mass in the y-axis, and similarly for the z-axis. Like, just as a quick reminder, a vector equation really means three independent yet simultaneous equations, right? That's number one. I'm just reminding you of that. And that's just true in general, right? But number two, also, this is sort of on the Shawnee thing. Oh, good, good. She's rocking. Right. Okay. I literally am going to do what Shawnee's saying, and that's awesome. I want to just add one qualification or one nuance. Like, notice that F net equals ma is a law about how forces work. It's Newton's second law of motion, right? It is not an expression of any one particular force. Like yesterday, last class, we wrote F equals negative kx. That is an expression, a function that tells you how a particular force works, the elastic force, the spring force, right? Just like last semester, we might have had F equals mu times the normal is a particular function that describes a particular force known as friction, right? This law, just to be clear, Newton's second law is not one of those. It's not telling you the nature of a particular force. It is saying what happens when you add all the forces up acting on an object, that the consequence of all the forces acting on an object produces its acceleration, right? None of the other force laws say anything about that. They just tell you how to get the force. In other words, getting to Shawnee's thing, other laws like F equals negative kx, like Monday's thing, they tell you what items, what forces, what expressions to plug into the left side of this law. This law is the consequence of all of those forces. The consequence of all of those forces acting together on an object is the acceleration. Okay? Yeah. So this is saying this, in other words, that big sigma that I keep writing is part of the law. The law is not strictly speaking F equals ma. It is sum of the F's, S-U-M, of the F's, or net force equals ma, the sum of all of them, right? So that's just, I'm not saying anybody's wrong about anything. I'm just like trying to establish that, because that sometimes still confuses people at this point. So therefore, if I go to step 4 now, if I go to step 4, PAW, particular application in work, the way we always know that I've transitioned to step 4 is I usually use the word here, meaning like in this case, here, the only force acting on the mass is along the x-axis, and it is the spring, or in other words, elastic force, right? I'm saying here, so add up all the forces, that equals ma, but here there is only one force. It's the spring force, and it's acting only along the x-axis. Therefore, here I do what Shawnee is saying. I say, okay, that negative kx force that we figured out Monday, that is what equals ma. Again, I'll say it one more time. So I'm agreeing with what Shawnee said, but the reason I'm agreeing, well, it's because it's right, but I'm agreeing because there happens to be only one force acting on the mass. Therefore, it constitutes the net force. Okay, so we do that. Then what we found out yesterday was that negative kx we found out yesterday, or we found out Monday, is negative 30 newtons. We know that the mass is 0.3 kilograms. So this is the work I'm doing in step 4, right? Negative 30 newtons equals 0.3 kilograms of mass times acceleration. So now I can go to the next thing and say, okay, step 5, final answer circled. And I could say, therefore, at x equals x naught, A equals negative 100 meters per second, right? And that's the answer for question 2. I'm just looking in the chat. Okay. Oh, that's a good question. Okay, wait. So, all right. So, I'll pause for a second. So, this is the answer, I believe. And yes, it is the answer. And I'll talk more about it in a second. But then someone's asking in the direct chat. You could put in if you drew a free. Okay, so someone's asking in the direct chat, why is there no mg in this case? It's a good, and they say they're a bit confused. Fair, totally appreciate the honesty. Good question, and they should submit for points. If you drew a free body diagram of the mass, you would have the F equals negative kx force going like this. You could put in an mg force as well. You could in the free body diagram. But the thing is, you also have, presumably, a normal force or something going up from the tabletop, balancing out mg, meaning from the presentation of this problem from the start, this was a mass that is just free to go back and forth on an x-axis. This is a horizontal spring. So somehow it's been either maybe not clear enough, but understood from the start that this thing is just going back and forth horizontally. It's not free to move vertically. This whole thing is on a tabletop, or so. In fact, I think that is in the picture. The whole thing is on a tabletop, or so. So in other words, this is, in this regard, this is not lab 1. Lab 1 is all of these aspects of a spring, but in lab 1, your spring was vertical. And mg did matter in lab 1. Your spring was vertical. And the reason for that is because it makes it much easier to make measurements and, well, just that. It makes it much easier to take measurements and data to make it vertical. And it turns out not to change the concept of negative kx in any way. But this is not a vertical spring. This is a horizontal spring. So even if we put mg into the free body diagram, it's being balanced out by the normal force for the table. So nothing is happening vertically. I don't know if that, you might want to tell me if that answer. Okay. Okay, cool. A good question. Okay. And lots of points and all that. Okay. So I think, okay, great. Thank you. And that's even more points because you closed it. All right, awesome. So this is the answer. Now, I'm going to move on in a second. I mean, if there are no other questions, but a couple of things to notice about this answer. First of all, it is negative to the extent that answer 1 was negative, then this is negative as well. It has to have the same sign as question 1. So assuming that left means negative and right means positive and I should have put that in my diagram. Assuming that I'm assuming this, then everything to the right is positive and everything to the left is negative, then this force, this acceleration is definitely negative. And that does not mean it's slowing down. It means it's speeding up in the leftward direction, right? So just note that. And also notice, yeah, exactly what Shawnee's saying. Right. And notice that that's a pretty big number. Like notice the question is at x equals x naught, what's the acceleration? At x equals x naught, the thing isn't even moving yet. Just note, note, its velocity is 0. It is not moving, yet it is accelerating. That is not a contradiction. It means it's about to move. It means it's changing its velocity from something to something. It means that if it were to keep going with this trend, that in 1 second, it would be going 100 meters per second to the left if we gave it a second to continue this trend. But I don't know that it is going to continue this trend. But so it is not moving, but it is accelerating, and it's accelerating to the left. It is speeding up to the left, just for what it's worth. Okay, so that's that question. All right, question 3 now. Sorry. No. Okay. Question 3. I'll do the, well, all right. I'm going to start accelerating, condensing or speeding up the 5-step method at this point. But let me know in the chat if you want more or less 5-step method. I mean, you have to do it either way, but so okay. All right, so for step 1, I just say steep diagram above. Step 2. The question for this one is at x equals 0. What is A, right? This isn't, yeah. Yeah. So this question is now, what is the acceleration at equilibrium? Notice, this sort of shows the importance. Notice how I'm tracking. Whenever I write a question and whenever I write an answer, I'm always including like a condition in the question and the answer. Like my last answer wasn't just A equals negative 100. It was at x equals x naught, A equals negative 100 meters per second squared. There's always a condition in the question. And that becomes really important, like right here, and really, because here, if you just look at the question I'm asking the same question again. I'm asking what's the acceleration again, and probably we're going to do the same method again to get it. So it's probably not hard, hopefully, if we just solve the last one, but it is going to be a different answer. This assumes that the acceleration is not the same at the beginning from what it is at the end. And yes, I do agree with Tony. All right, so I'll keep it. Awesome. Right. So it is the same method as before. So 3. Same thing as before. Right. So here now we're talking about when x equals 0. So yes, here. Okay, so this is the final answer. Like she said, sorry, I'm really, okay. So the final answer is at x equals 0, A equals 0 meters per second squared. And just note that too. Number 1, it seems that we're saying the acceleration is different at every different spot. That's important. Number 2, just like at the beginning, at x equals 0, we were saying the thing wasn't moving, but it was accelerating. Now I think we're saying the opposite. At equilibrium, like this thing has moved in now, right? We let it go. At first it wasn't moving, but then it got moving faster and faster and faster and faster, moving all the way toward equilibrium. Now when we take a snapshot of it at equilibrium, it's moving fast. Like it's been building up speed since the beginning. So it's moving at some unknown but high speed, but it doesn't have any acceleration. right? So just note again, I don't know if this is confusing to you or not, but it is noteworthy that in the first position, it had no motion, but it had acceleration. Now it has no acceleration, but it has motion. So acceleration and velocity are not the same thing, if nothing else. Okay, so that's question number 3. Now let's go to question number 4. Okay, so now careful, wait, careful. That, okay, and I think wait. Okay, hold on. Good question in the direct chat. Someone's asking, do I want you to mark down the 5 steps or just write everything down as per steps? Very good question. So ideally, I think it's better for you and for me, especially as you get used. I think it's better if you mark down the 5 steps. Just to be clear, technically, if you did all the 5 steps, but and say it was an exam, if you did all the 5 steps, but you didn't mark them, I wouldn't like take off points for that. But it makes it a lot easier to make sure that you're getting all the points if you do label them. Like I highly recommend that you label them, is basically what I'm saying. It's a really good question. But now I want to say for this next one, I think we need to slow down a little bit. Like I'm psyched that you guys are keeping me going fast. That is good. And that you're showing that you know what's going on in the chat and everything. Like that's awesome. But actually, now we're going a little fast because I actually don't totally agree. I sort of agree with sort of what Shawnee's saying in the chat, but I think we should be careful, like slow down, because I don't mean that critically, but like I don't actually agree. I wouldn't want you to copy down what's in the chat. Let me put it that way. Like there's something right about that, but that's not but it's deceptive. And frankly, question 5 is very similar to question 4. All right, so we're going to slow down for a second. Yes, we're getting into energy and work now. Yes. And ultimately, I'm going to have a lot to say about work and energy and potential and kinetic and all that. It is true that right now, today, first, I'm just going to sort of do it out and give you the answers and show you what I would expect on the work, like sort of like what Shawnee's doing. That is true. But I'm also going to say question 4 and question 5 now, like we're on question 4, but question 4 and question 5 both will have the same GDP, the same general concept that's going on, which is energy conservation. They'll have the same GDP and the same approach, but they'll get different answers. But just to caution you, if you were to literally write down what's literally in the chat right now as the GDP, that would look like it would work for question 4, but it would end up getting you a wrong answer for question 5. So I want to be very careful. I'm not saying this critically. Well, yeah, okay, so slow down. All right, oh, you're welcome. I was about position speed. Well, all right, so you did it using derivative. Good. I mean, wait, derivatives or integral? Well, we'll see. All right. So, okay, what am I trying to say? Well, we'll see how you did it and we'll see how I did it. Uh, okay. Well, all right, so let me so yes, it is, question 4 says, what is the speed at a given spot? Like, what is the speed at a given position? And then question 5 says, what is the position for a given speed? They are conceptually very similar questions on purpose. They're sort of, one is just the reverse of the other. One says, given a certain position, what is the speed at that position? The other one says, given a certain speed, at what position would we find that speed? So the method is the same, yes, and it's the method I'm about to show you, yes. But that method you have to be careful about. Otherwise, If you're otherwise, it'll only get one of them correct and not the other. Wait, using derivative. All right, so slow down. So let's see. So let me derivatives with respect to time. Well, we'll see. Wait, so one thing is I don't think we know anything about the time yet. All right, so I'm totally psyched for this participation. Don't get me wrong. And like Shawnee's getting tons of points for saying all of this in the chat. Like it's awesome. But yeah, let me sort of show you my thoughts and we'll see how they compare to your thoughts. Okay, so we're talking about question 4 here. Question 4, and the question is at x equals 0. Right? That's the question. And notice the progress of this, like the progression of this. Like first we were looking at the end point over here. We were asking, okay, what's the force? What's the acceleration? Then we sort of in our minds tracked the mass as it moved in toward equilibrium. And then at the equilibrium, we're asking, okay, what's the acceleration? Now we're asking, what's the speed, right? We know the speed way out at the edge, it's 0. Now we're asking, what's the speed at equilibrium? And this is now a harder question. It is. Than anything we've done. I'm not saying it's hard. I'm just saying it's harder. So step 3. Well, okay, slow down. Wait. Oh, okay. Wait. Whoa. Wait. Okay, one thing also to caution you, and I am really psyched about all this participation. I am going to look at what's written out. I am, so don't take this the wrong way, please. But like this thing of a times the square root of k over m, I'm not saying that's wrong. I mean, it's not wrong, but that's the kind of thing that if you put that down on the homework right now or in an exam, like just right as it is, just right there, I would write WWW on that, which stands for like what, where, from, why, or what, why, where, from, meaning, hold on a second, that equation seems out of nowhere. I'm not saying it's wrong, but it's certainly not any equation that we've developed, or it's not, put another way, it's not a GDP. It's not a general definition or principle. It's not a law or a first or an axiom or any concept that we've established or that we have any reason to believe yet. It's some kind of equation that someone's derived from a bunch of other equations, and it does exist on the web. And I'm not saying it's wrong, and I'm not saying you can't go on the web. But I am saying to everybody, that's an example, if I may, and I hope we're all like friends at this point, that equation, a times the square root of k over m, like that has to be justified. You're allowed, you can use whatever you want if it makes sense and you show how it makes sense and you show how it makes sense to you. But that is definitely an example of something where if we're going to use it, we better show how it makes sense, because as it is, I don't know. I mean, I do, but like I don't have any reason to see where it's coming from right now. Now, similarly, wait, as long as we're, wait. We are going to end up using something like what Katie's writing. Okay, all this participation is great. We are going to use something like what Katie's writing and like what Shawnee said, like a couple of like lines back in the chat. But again, even those things I have to explain, and we have to use them correctly. We have to be careful about them. Like basically, I don't want to say kinetic equals potential. I mean, to cut to the chase, I'm going to say things about kinetic and about potential, and different people are at different levels of knowledge of those concepts. But the one thing I don't want anybody, what you don't want to ever memorize, what people do, what is a common misconception, don't go around memorizing kinetic energy equals potential energy. Like that is true under the rarest of circumstances. It is not in general true. And it's like definitely not true in question 5. And when it is true, it's true in a very specific way that does not capture. So again, I'm not criticizing. I'm just, as long as we're trying to learn this, I'll tell you, remember, a GDP is supposed to be a thing that is true in general, not something that's derived for this particular example, but something that's true even before the example. So I don't think saying kinetic equals potential is something that's true in general. I will show you what I think is true. Oh, wait, what was the thank you? I don't even know what the thank you is, but you're welcome. Here. Oh, wait. Right. Okay. Sorry, I'm looking at the chat because I mean the chat is popping and buzzing, which is great. All right, and obviously I have to start. And then Shawnee said, this is what I wrote out, but I don't actually see anything written out, but that's okay. Wait, that is correct. Wait, not always. Okay. You're right. Okay. And just again, I'm just trying to respond to the chat because like it's better if it's like you guys than me. So uh, 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 I do agree that I'm going to say some part of what I'm going to say is definitely related to what Shawnee's saying and related to what Katie's saying. Like I am at some point going to use something like PE equals 1 FKX squared, but I have to show you where that's coming from, number one. And number two, yes, to be clear or to be fair, like Shawnee's saying, that's not always correct. I mean, but it is correct here, yes. But so we have to be careful about that. This is like the difference between step 3 and step 4, et cetera, et cetera. All right, so I'm going to do it. Hold on, I'm just okay. Okay. First thing is, let's say, and now here's me being a teacher for a second. We're about to do step 3, GDP, right? That's supposed to mean things that are true, principles and definitions that are true even before the problem started, like laws, definitions, right? So, for example, and this is where like thinking comes in, right? Let's say this were an exam right now. Maybe I don't know just yet what general definition or principle to use. I could write down something like F net equals MA, because like I just wrote it down before and it was true. I could write it down. You could write it down. And it's true. It's a law. So if you wrote it down on an exam or homework, I would give you points for that because it is true. And it's like super important. That doesn't mean you're necessarily going to end up using it here, but you could write it down as a way of keeping your, like, until you realize you're not going to use it. Writing it down helps, right? Similarly, I'm going to put this in a different color just so I'm not confusing you. Similarly, right now, you might think something like, you look like you don't know what to do, let's say, for a moment at home or in an exam. You know you're looking for V at some point, and you know you have A at some point, and you even have X at some point. So you might be thinking of equations that you remember from Physics 203. You might be relating, like trying to remember equations that relate X to A to T to V naught or something. And this is getting to one of the things that Shawnee, I think, was saying in the chat. You might try to write down and remember some equations that relate those things, like X equals 1F AT squared plus V naught T. Now, notice I'm writing in a different color, so I'm trying to make a point here. You could write that down, or you could even then look at it and you might even go, oh, that's true. But like you write it down to keep your brain going, right? So you write it. And let me say, that is a true statement. So if you wrote it down, I would give you points for it. I would not, it's not wrong. You wouldn't lose points. But then, and one of the reasons I would reward you for writing it down is by writing it down, it then forces you to look at it and you could be like, and again, maybe this is what Shawnee was saying before. You might look at it and go, oh, well, wait a second. That might be true. Like, thank you, Yaverbound, for acknowledging that it's true. But I don't know anything about T in this situation. Like it's true, but it's not useful, you might say, because I don't know anything about the time. So forget that, right? Okay, so that just means fine, good. The fact that you wrote it down helped your brain realize something. So you might write something else down. You might write something like this from Physics 203. Like that's a true equation from Physics 203, and it doesn't have any time in it. So it starts to look a little bit more relevant to what we're doing right now. So you might write that down, right? Okay. And again, I would give you points for that because you are like advancing, you're like pushing the ball forward if you write that down. But now, here again, here's what I think some of you are like already realized or whatever. The thing about writing that down is it makes you realize the key point. Oh, someone's here? Oh, sorry. Okay. The key point in writing those things down is that by writing them down, they make you realize what's going on in the problem and what is actually challenging about it or what needs to be addressed, which is by writing those true statements down, those true statements that have A in them, like then you would start maybe going to like plug in, okay, what should I plug in for A, right? Like it looked like especially that second equation looks totally reasonable. So then you might go like, all right, what am I going to plug in for A? But then you realize, well, wait a second. At x equals x naught, I have one value for A that I just got in question 2. And at x equals 0, I have a different value for A that I got in question 3. A is not constant. All of those equations that we learned at the beginning of Physics 203, those are what you might remember. They're known as constant acceleration equations. They are all equations that assume a constant value of acceleration. They assume some number that you could plug in for A. And by writing them down, that's what you realize is the issue. And it is the issue. I'm not trying to trick anybody. And I'm also not off the topic. Like this is the topic of this like whole sheet, is that now for kind of one of the first times like in our life, we have a situation that looks fairly straightforward. Like the force is just negative kx, not that bad. Like it's a straight line force. It doesn't look that great. It's like a mass on a spring going back and forth. But what we realize by writing these things down, by searching for a step 3 GDP, we start realizing, oh, the hook of this problem, like no pun intended, the issue of this problem is, oh, we don't have constant acceleration. Our force is changing at every position. Our force is changing. Well, I'm gonna write that down. Okay, the thing that I'm saying right now as a GDP, like in English, because GDPs can be in English sometimes, or at least, yeah, I mean, a general principle here is when we face a problem, when we realize that the force is changing from place to place and changing continuously, right? Like it's not a cartoon. It's not like over here the force is one thing and then right over there the force is another thing. No, like smoothly, continuously, every millimeter that mass shifts over, the force shifts over by a certain number of newtons, right? And that's what's making this problem actually worthwhile. It's like actually what makes the problem deep and challenging and why we're talking about it for like a long time. Whenever that happens, that's when we shift our attention and our thinking from Newton's second law, from forces and accelerations to work and energy. I'm going to say that one more, I'm going to say it a different way in a moment. And I'm saying this, and I apologize if this is boring anybody or whatever, but this is like a big, when I was in college, when I could get to the point where I could do a lot of the work and the work and the energy equations and stuff, like just like many of you, like I could do them. I knew like KE equals 1 FMV squared, whatever. But the thing that always eluded me when things started getting hard is I never freaking knew it always seemed a surprise to me that the professor would just like suddenly start talking about work and energy when I thought we were talking about forces and accelerations. Like I got like, and they never knew how they knew which one to talk about when, right? And I'm telling you, number one, a key point is when the force changes from spot to spot, that's when you shift your attention into the work energy model of physics. Okay, that is number one. More specifically, so I'm looking at it. There is going to be a differential equation, just to answer what's in the chat. There is going to be a differential equation, but that will come in the very last question of this whole homework. A very important, very good observation, but I don't think there's any differential equation going on here yet. I think there is an integral, but no, so I mean, good question. I don't know if that answers it. So what I'm saying is more specifically. Well, here, sorry. Next page. Now, again, I'm still in step 3 here. I'm giving you the general definition or principle that applies to this problem. I'm going to write it mathematically next, but I'm just trying to build it in English first because we haven't talked about it yet. So what I'm saying in English, hello. Okay. What I'm saying in English is, so just to be clear, I'm still in step 3. Okay. Again, this is English. I'm about to give you the equation for this. But what I'm saying in English is I'm saying, I'm saying in English what it says, when all the forces doing work on a system are conservative forces. Now I have to define that for you. And I will, of course, but in a moment soon. Um, okay, when all the forces doing work on a system are conservative forces, then the system will conserve total mechanical energy. Now, well, okay. For the moment, I'm going to define soon what I mean by conservative force, but interesting. It's actually a slightly deep, slightly non-obvious definition, and it's mathematical. So I'll get to that in a few minutes or on Monday. But for the moment, what I'm telling you is a list. I'm saying there are certain forces that are called conservative. The forces that are on that list are the elastic force, i.e., F equals negative kx, the Hooke's law force, the gravitational force, i.e., mg or gmm over r squared, if you're like in outer space, and the electrostatic force, which we have not yet discussed in this class, but which becomes a very big piece of this class, like in the second half of the class. Those forces are known as conservative forces. Again, I will get to like why soon, but they are. So whenever any combination of those forces are doing work, and examples that are as opposed to, just to be clear, I'm sorry, as opposed to like the frictional force or the normal force or the tension force just to provide a clear contrast, these are not conservative forces. If you want a quick if you want a quick like way of sort of picturing what the difference is between a conservative force and a non-conservative, the quick way to sort of see the distinction I'm drawing is that any force that we call conservative always is associated with some kind of equilibrium. Like springs are always trying to bring you back to the middle, right? Gravity is always trying to bring you to the ground, and protons are always trying to bring electrons to them, or or vice versa. So with conservative forces, there's like a preferred position. There's a position that is more stable than other positions. That you can rely on that. That's still not the strict definition, but it is a hallmark characteristic. So whenever, unlike friction or the normal force or tension, which don't want you to be in any particular place, right? They just like pull or push or whatever. So the truism that I'm saying to everybody, first of all, in GDP is, if we know that all the forces that are doing work on a system are conservative forces, okay, and we do, in this case, the only forces doing work here is the gravity, is the elastic force, the spring force, right? So the only force that's doing work here is conservative. Therefore, we can say that this system will conserve total mechanical energy. Now, what does that mean? Well, conserve means maintain constant value from position to position, like from place to place. Let me be clear about this. Now, again, I'm writing a lot. I'm going to remind you again, in principle, everything I'm saying right now is all about step 3 GDP here. I'm not saying you in your homework or your exam would write every single one of these words down. Like, I'm dragging it out a little bit because I'm teaching you something, or, because I'm trying to clarify and teach you a concept that we have not talked about yet. Like, this is the first time I'm introducing this concept here in this class, so I'm saying a lot. Similarly, you, with your homework or an exam, if it's the first time you're introducing a concept, you want to go a little bit overboard, right, to make it totally super clear. Right? Now, once it's established, then for the rest of the homework or the rest of the exam or whatever, then you can shorthand like I'm going to do. But so I'm not trying to lose anybody. And I know there's 17 minutes left. I will get back to actually answering the question, like I will momentarily. But I'm saying the concept here is that as long as all the forces doing work on a system are conservative, then the system will maintain the same amount of total mechanical energy from place to place. And that is key. Again, that is something that eluded me for years. When we say conserve, I know you all know that conserve means maintain constant, right? I know you know that. Conserve means the same. But there's many different types of same in physics. You could be the same amount from time to time, or you could be the same amount from place to place. For example, when we're talking about energy, we mean specifically, explicitly, always, we mean from place to place. This is all about, well, I'll say this, remember, this is all about a situation where force is changing from place to place. Like we're using the concept of work because work is what we constructed to track the effect of a force acting from place to place. So our truism here is about to be, and we will solve this problem by the end of this class. I promise you. There'll still be more to say about it next time, but we will get the answer. I am saying that if all of the forces doing work on a system are conservative forces, such as the spring force or the gravitational force, then the system will maintain the same total amount of mechanical energy from place to place. And what do I mean by that now? To start getting to like what like Maria was, or like Katie was saying, and Shawnee was saying, and other people were saying. So here comes so to put this in mathematical terms now and to start solving, when I say conserve total mechanical energy, the conservation of total mechanical energy, which I will abbreviate with capital E, the way to write it as like a GDP or as an equation, what I'm saying is E at any one spot must equal E at any other spot. Okay, the total mechanical energy over here at some spot that we know everything about, such as X equals 0, must equal the total amount of mechanical energy at any other spot that we're solving for, such as X equals, I'm sorry, that was such as X equals X naught, must equal any other spot, such as X equals, sorry, excuse me for a second. Such as X equals 0, right? The total mechanical energy must be the same at both spots. And what do I mean by the total mechanical energy? By definition, I mean the sum of all of the kinetic energy at that spot, plus all of the potential energy at that spot. So if you're looking, so if you're looking for this GDP to be expressed in mathematical terms, I'm saying in a situation like this spring here, all the KE plus PE over here must equal all the KE plus the PE over there. Okay, so this is still G. So now I'm going to start applying that. So that's step 3. That's your GDP. But now to apply to this problem, I'm looking at step 4. Here, okay. Here, kinetic energy at any given spot equals 1F mv squared at that spot. You could make a note of that or flag that or pin that, because in theory, you all know that from last semester in theory, but it was rushed for many of you by me last semester. So it's maybe still sort of new to some of you. So I will expand on why that is or what that's all about more on Monday, but it's true. Okay. In fact, that you can take to the bank, that kinetic energy for any circumstance that's ever coming up in this class, it is a promise. Any circumstance that ever comes up in physics until 1905, kinetic energy always equals 1F mv squared. If you're going to memorize anything, you can memorize that. Like that is reliable. Kinetic energy always equals 1F mv squared. Now, I am going to explain it more on Monday, but it's true. But potential energy, now again, here we got into the Katie thing and the Shawnee thing, and I'm not disagreeing with any of them. I'm just like now trying to like put it my way or whatever. Like that is true always, always, okay. But potential energy differs from situation to situation. In general, we have to talk deeply about potential energy. We have to talk about it in terms of integrals and calculus on Monday. We do. It's not a joke of a concept. It differs from situation to situation. But to cut to the chase so that we have some answers and some like concreteness before the weekend, I will say here, in the case of a spring, of spring potential energy, spring potential energy does equal 1/2 kx squared. Again, I'm fully aware and fully giving credit that like Shawnee said that, or something to that effect, and Katie said that, and that is true. I want you to make a note, like this is to be explained. I do not think that what I just gave you was an explanation. I just think I gave you a fact. But it is a fact. Okay. So, and again, like for example, potential energy due to gravity is not 1/2 kx squared. Potential energy due to gravity is mgh. Like, and if gravity were relevant in this problem, as somebody in the direct chat asked like minutes ago, then we'd have to deal with mgh. But here, all that's relevant in this problem, the only force that's doing work in this problem is a spring force. So the energy that's relevant in this problem is 1/2 kx squared. Again, I'm going to explain that in more detail on Monday. But so, okay, I'm just looking at the chat. So what this all means is that therefore here, I'm still in step 4 now, right? Here, what I'm saying is, if you're solving it, and here's where I'm getting a little, this is where I want to slightly correct something that was in the chat. I would say, therefore here, if you're following the logic of this, we're saying here, 1/2 mv squared plus 1/2 kx squared over here at some spot that we know everything about, that would be x naught, must equal 1/2 mv squared plus 1/2 kx squared at a spot that we're solving for, which is x equals 0. Right? Notice, and we're going to plug in the numbers, we're going to get an answer, and we're going to like have a nice weekend. Well, first you're going to be tortured for 2 days, but like notice really after I'm talking because I'm trying to teach, but the GDP that's really going on here, if you were to just like cut straight to equations to solve this problem, what the first thing to write is 1/2 mv squared plus 1/2 kx squared over here at some known place equals 1/2 mv squared plus 1/2 kx squared over there at some other like solving for place. Right? Don't write 1/2 mv squared equals 1/2 kx squared. Like, don't start with that because that's not a principle. This is a principle. Specifically, this principle, I'm writing this just as a note, as a teacher or whatever. Mechanical energy conservation. Mechanical energy conservation is always a speed to spot correspondence. Like, this is true. In other words, what the whole point, the whole thing of mechanical energy conservation is, if you know the speed at a certain spot and you need to know the speed at a different spot, or you know the speed at a certain spot and you need to know the spot at which some speed occurs, then you use mechanical energy conservation. What I'm really trying to say is mechanical energy conservation is what we do when we're totally end running any issue of time. We don't know anything about the time. We're not solving for anything about the time. We have a paradox of like the force is changing every single spot. Whenever we know the speed at one spot and we're looking for it at a different spot, we use energy conservation. That's what's going on here. All right, so I'm going to keep filling in. So I'm still in step 4. I'm filling in now. I'm just going to rewrite. So we have 1/2 mv squared plus 1/2 kx squared at x equals 0 equals 1/2 mv squared plus 1/2 kx squared x equals x naught, right? I'm comparing one spot that I know to a spot that I know. So first of all, I can factor out a 1/2 from each side. I can factor out the 1/2 and divide both sides. So the 1/2s go away, right? And then notice this trick too. Again, I know there's 6 minutes left. We're at least going to get this answer. And I'm going to tell you the answer to number 5 when we're done too, so you could test yourself. But one trick too, again, for people who, especially for this class, especially for Physics 204, habit that you want to try to get yourself into in all of these step 4s. You're not going to like it at first, but try to postpone numbers for as long as possible. Don't plug in the numbers and then do all the algebra, even though that is more tempting to most people and more comfortable. Try to do the algebra, solve for what you're trying to solve for, and then put in the numbers at the last minute. There's many reasons for that, not the least of which is the more this course progresses, the numbers are going to drop out. This course is going to start looking very abstract and very mathematical to a lot of people. So you want to get used to being able to handle this stuff without the numbers. So what I mean by that is, I'm solving. What am I solving for? I'm solving for V at x equals 0, right? So I'm going to so I'm solving for V. So let me just treat this like an algebra problem. And sorry. Well, yes, I am saying that, but also there's one more thing I can do before I do this too. And this is where people get into, like, I could also cross out some terms. Like when X equals 0, X definitely does equal 0. So that whole term goes away. And when X equals X naught, on the other side, V equals 0. So that whole term goes away. This is where some people then think 1F mv squared equals 1F kx squared. Like it happens to be true now. Now I'm going to, in other words, now I'm saying, yes, here in this case, the mv squared over at this spot does equal the kx squared over at this other spot, but don't memorize that because first of all, we're not saying kinetic and potential are equal to each other. We're saying kinetic over here is equal to potential over there. And second of all, you will see that if you were to write this down for question 5, you'd get the wrong answer. Like you don't want to start with this. This just turned out to be the case because I crossed out some terms with zeros. But now I'm solving for V. So I go like this. And again, and this is totally what Shawnee said in the chat. I totally saw it. It's great. Like she said this, it's true. I just wouldn't want to start with this. I want to make sure we see that, right? And then we plug in the numbers, which is 200.15 squared. You should put in the units, but I'm going fast because I'm looking at the clock. And 0.3 at the bottom, right? So then we get for step 5, FAC. What we finally get when you plug in the numbers in a calculator at X equals 0, V equals approximately 3.87 meters per second. Like that is the answer. That is the answer for question 4 that is done using energy conservation. I'm going to say a lot more about the integrals underlying energy conservation on Monday, but this at least like helps a lot with the homework. And I'm going to say now, because there's 3 minutes left, for question, and obviously stop me. Wait, is it? No, good. And I believe you. I know Shawnee had this answer. Like I totally, and that's great. Like for real. But now to be super clear, we're going to end this one for question 6, right? Question 6, which is question 6 says, when V equals 3 meters per second, what is X, right? Question 5, question 5 flips this. It's the same concept, speed, spot, correspondence, but now it's giving you a speed and asking you the spot. So for sure, so I'm going a little fast now just so you can make sense. So for sure, the GDP is the same. The GDP, again, the GDP, this is what I want to emphasize. The GDP is 1F mv squared plus 1F kx squared over at one spot that we know equals 1F mv squared plus 1F kx squared at the spot that we're looking for, the spot that, or sorry, I'll put the other way around. The spot that we know compared to the spot that we're looking for or solving for, which is X. Like we don't know what X is. That's what we're solving for. That's the GDP to start with. You will cancel out the halves, yes. And you'll cancel out one of the terms. You'll cancel out that, but you won't cancel out a term on the other side. If you think this through at home, you'll realize you can't say 1F mv squared equals 1F kx squared for this one. And you never want to start with that. If you then plug in the numbers and just proceed as before, you'll know that you've done this right if in the end of the day, you get as an answer for this one, and this is where we're going to stop, but I'm just telling you, the answer for this one is X equals approximately 0.095 meters. And strictly speaking, it's a plus or minus. We can talk about that on Monday too. Like it could be on one side or the other side, but it's 0.095 meters. If you got 0.116 meters, you're not crazy, but you are making a mistake. If you got 0.116, don't feel ashamed, don't feel embarrassed, but do understand that this sort of like entire lesson was catered toward you in a way. So 0.116 is the most common mistake. The correct answer is 0.095. If you got that or you get that for question 5, you're on top of things. Class is just about over now. 6, 7, and 8, the next 3 questions, which we'll go over on Monday. You don't have to do all the 5-step method for them. They're more conceptual English, but you have to show thoughts. You can't just put answers. You have to explain your reasoning for the next 3 questions. And then 9, we're going to talk a lot about. So bear with me. You're being very patient in it. You obviously have more time to do this homework or revise, upload, blah, 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 blah. I'm going to end it. You could go have a nice community. I'm staying. If there's any questions at all, I'm still here and I'm turning off the recording. Bye. Yes. Good. Oh, good. Oh, good. That's great. All right. Sorry. I saw, okay. Okay. So I'm pausing. I'm here, still here. I'm just turning off the